Hello everyone and welcome to this 13th lecture of this course, and in this particular discussion we are going to have a discussion on georeferencing technique. This is very important processing both in digital image processing, and that is means in remote sensing as well as in GIS. This is a common thing which has to be done to all types of data sets which are not so far belonging to geographic domain, and that is why the georeferencing is very much required. It is a serial processing or a step by step it has to be followed, and it is not complicated, but it is very important technique in remote sensing as well as in GIS. So, if I look the definition, what it says that the georeferencing basically transforms image data maps from one domain, that is geometric domain, to geographic domain. Geometric domain, if you recall the coordinate geometry which was taught to us in somewhere in 9th 10th class, introduced in 9th 10th class, that we used to have a in the corner of two axes, in the origin we used to have 0 0, but if I go to the downward or on the left side in my coordinates, then these becomes negative, and then complications will start once I go for measurement of a length or an area or perimeter, if I am having half coordinates in positive, half in negative, and so on and so forth. So, this coordinates, the concept is same, only this the coordinates have changed. Instead of having 0 0 in the origin of two axes, we are having geographic coordinates which are continuous all over the globe. So, we transform basically maps, satellite images especially, because those satellite images can be corrected to some extent using orbital parameters, but those are not very good inputs for a very accurate georeferencing. For relatively coarser resolution satellite images like NOAA HRR images, even this navigational or orbital parameters, if I use for georeferencing, may be for some applications may be appropriate. But as we go for higher and higher spatial resolution, more accurate georeferencing is in demand. Then we are looking for very highly accurate georeferencing process or technique, and therefore we need to transform our satellite images, whatever they are coming from different satellites or maps, because on GIS platform we handle lot of maps also. So, these maps, if I say scan a topo sheet, a survey of India topographic map of say 50,000 scale, now it will have the image will have at the top left corner will have 1 basically from first pixel, and then everything whatever it is there, and this will remain in geometric domain unless we go for georeferencing. So, that is why all these maps, if they are scanned, they will be in geometric domain. Images also more or less are in geometric domain, especially high resolution images I am talking, and we need to transform from one domain, that is geometric domain, to geographic domain, and this georeferencing technique will allow you to bring coordinates in our images or in our maps of geographic coordinates, that is in terms of latitude longitude. So, that is the basically purpose of georeferencing. As I have mentioned that when an image, a satellite image is acquired, the resulting image has certain errors, systematic and non-systematic errors. In very soon we will be seeing which are systematic errors, which are non-systematic errors, and then these geometric errors will create distortions in the images. These distortions in the images might come because of scan skewness. Scan skewness comes because your polar orbiting satellites or remote sensing satellites are not exactly orbiting from north to south, they are having a near polar orbiting, and therefore and at the same time when scanning is done by the sensor or a satellite based sensor, earth is also moving. So, therefore, there you will have a skewness, which we will see very soon what the basically skewness is. Maybe a panoramic distortions are because your satellite having say relatively poor spatial resolution, data might be covering a very large part of the earth. That means the swath width, if it is large, then the curvature of the earth will also play a very important role, and then your images might be getting distortions because of panoramic distortions, maybe attitude of platforms. These satellites are moving objects in space. So sometimes there might be change in the velocity, they might tilt in one direction or another, and therefore they might bring these kind of errors in the data like velocity, altitude, pitch, roll or yaw. All kinds of errors are inbuilt in images, in satellite images. But using one georeferencing technique, many of such errors, especially systematic errors, can be removed quite easily. So that is the beauty of this technique. Is few systematic errors which are easy to remove. Systematic errors, cross-check scanner in earlier like in Landsat programs, we had these cross-track scanners. So they used to have distortions in the images, especially on the edges of image. So that was the reason. Now we are having more linear arrays system based long track scanners, and therefore these errors have been minimized. Then mirror velocity, because in these errors we used to have optomechanical devices as discussed in earlier lectures when we were discussing different sensors and platforms. So they used to have a moving mirror, and that mirror used to have some variations in the velocity which might caused some distortions in the images. So in earlier versions of these Landsat MSS images, all these kind of errors were there. Skewness problem will also be there, as I have mentioned that when satellite is orbiting not in near pole to pole but near polar, same time earth is also moving, and within that one say a scene is about say 10 minutes are required to capture a scene of say 150 kilometer by 150 kilometer area by a moderate resolution sensor. Then in that 10 minutes there will be some movement of the earth below the orbit, and therefore this will cause a skewness. That is why you see in the images. The non-systematic errors which are difficult to predict and which might be there, sudden change in the earth rotation. Of course this is a more or less a known thing, but altitude variation of the satellite, pitch variations of the satellite, spacecraft velocity, suddenly it has changed, slowed down, it may create some problem. Roll, that means your platform has rolled over like this kind of movement, so that will create a rollover, or yaw means it has moved something like this in a space while moving or while scanning or acquiring the satellite image. So therefore these kind of errors might be inbuilt in the data. So many of these errors through georeferencing can be removed quite easily. As you know that images are stored as raster data, that means the two-dimensional matrix, which each pixel in the image has a row and column numbers and hence are in geometric coordinate system. So top left we start counting top left the first pixel first row and so on and so forth. And in order to display and analyze these images in digital image processing or on GIS platforms, we need to have a georeferencing maps or data sets. That means we need to have at least somewhere for referencing, something for referencing, and that is necessary to establish an image to word transformation. So we need to have a master image or master map, and then if I use a word slab, the map which is in geometric domain, the image which is in geometric domain need to be transferred into geographic domain, so that you need to have something which is already in georeferencing or georeference or geographic domain. So this image to word transformation is possible, and then your image can be converted, image coordinates which are row and columns can be converted to in real world coordinates, that means the geographic coordinates, and that also means the latitude and longitude. So a common method of georeferencing, also it is known as geometric corrections, image registration, image rectification. So, in different books, literature, you may find little different terms. Nowadays, the most popular term for this kind of processing is called georeferencing, is to statistically find a polynomial of a given order. Depending on the distortions which you are expecting on an image, you would choose appropriate polynomial equation, and then that will minimize the errors in a transformation from a original image coordinates to rectify image coordinates. We will see little later all these details, and then once this transformation function is found, that which pixel has to go where, then the next thing is to we go for the least square fit for coefficient of a given polynomial equation using ground control point that are picked by the user. And once this is there, the transformation is there, then the last and third step is that you go for georeferencing. Let me give you through this schematic that this is input image which is already in geographic domain, that is it is georeference, I consider as a master image. And this is this is my reference map, master image, this is input image which is having skewness effects are visible here. So, this is raw image, this is master image. Now, these are the ground control points. What are the ground control points? Ground control points are those points which are common visible in both my image and say in a map. So, suppose if I say this is my survey of India topo sheet and this is my satellite image. So, if I am seeing the crossing of two roads or maybe a bridge on a river, maybe a bridge on a rail track or a aqueduct or similar kind of structures which are fixed, which are not moving with time very quickly. So, these may become my ground control points, and we say common ground control points means if I am seeing roads of two roads cross section here, then the corresponding road cross section should also be visible in my map. So, I will note down the coordinates from my master map or reference image and then use and assign these through my polynomial equations, assign these to these unknown location which I have already identified, but only coordinates are missing. So, this image will have geometric coordinates, will start from top left. This image master map will have my coordinate, geographic coordinates which might start from bottom left. And once it is done through resampling, then I will have which this raw image will fit over my master map one through after doing resampling, and then finally I get a product which is geometrically corrected. That means it is now having geographic coordinates in it, and it can be used on a GIS platform, it can be pasted on Google Earth and so on and so forth. Now, which order, polynomial order to choose? But before that, let me reiterate three steps. First step is registration. Registration of an image or a map which is slave with a master using ground control points. Once this is done, then I choose once it is registered as per my polynomial, as per the requirements, as per the distortion present in the image or expected distortions, I will choose accordingly the polynomial equations. And these polynomial equations with least square fit will give us the transformation function. Now, transformation function means that which pixel will move in which direction and how much. And once I know this much for each pixel of my slave image with reference to master image, then the third and last one is georeference and resampling, and that means there are three techniques of resampling. And then the value of the pixel, what values should be assigned to a empty master map which is going to be my final georeferenced map or image, and that can be decided by during the resampling step. So, three steps: first the registration with using ground control points, then using polynomial equations, finding out the coefficient or transformation function, and finally going for resampling. So, now which polynomial equation? The first order polynomial is required which also called as a conformal polynomial, when I have to transform from just simply from geometric domain to geographic domain. So, suppose I am having a map which is not yet georeference, I just would like to simply transform without change in scale, without any rotation or without any removing curvature of the earth or anything. Just simple transformation from geometric domain to geographic domain, then first order polynomial would be more than sufficient for this kind of transformation. But in case of satellite images, this is not sufficient at all, because it involves not only just simple transformation from geometric to geographic domain, but might be change in scale, might be rotation as well. So, if that kind of requirement is there, then the second order polynomial will be chosen, that is also called affine transformation. So, instead of just transferring from one domain to another, second order polynomial equation will allow us to transform not only from geometric domain to geographic domain, but also it will allow us to change the scale and it will allow us the rotation of my map, so that I get north completely upward. So, that for that purpose the second order polynomial will be chosen. If I am having a relatively coarse resolution data and this satellite image requires corrections, not only the transformation, not only change in scale, not only rotation, but same time this curvature effects has to be removed, because satellite image is representing a curved surface of the earth. If it is a coarser resolution image, for example Novaya Vichara data, which is covering a 2800 kilometer in one swath, one go, and this width of an image is covering a curved part of the earth, and that has to be unwrapped, basically it has to flatten, and therefore for such kind of images where we expect that they might be suffering from even few more distortions, not only scale change and rotation, then third order of polynomial is appropriate. Though in some softwares, in image processing or in GIS softwares, people have implemented up to 12th order polynomial order, but I do not think that such kind of georeferencing is required, because maximum what we can see the distortions is all because of curvature of earth or rotation of a platform, yaw and roll, other things are there, or this is skewness. All these can be corrected at a third order polynomial. But if you go higher and higher in the polynomial equations for determining the transformation function, then the number of GPS would be much higher. So, this is decided based on the ground control points, and that is, and based on this equation, P is the polynomial equation. So, if I choose for first order of polynomial, then number of GPs as minimum number of GCPs are required only 3, but if I choose 2, then second order polynomial, then I require 6. If I choose the third order polynomial, then minimum number of ground control points are required 10, and so on. That does not mean that if I am going to, for georeferencing, I will only choose, if I am using the first order, I will only collect 3 ground control points. No, that is the minimum requirement. In practice, we go by multiplying 2. So, if I am going for first order polynomial, instead of 3 ground control points, I will choose 6. If I am going for second order polynomial, instead of 6, I will choose 12, because I want to achieve georeferencing within pixel, and for that I need to choose ground control points very carefully and corresponding point in my slave map 1, and then I should choose more ground control points, so that my image rectification becomes very accurate. This is how once again I am trying to explain here that one map here is the my slave map, another one is my master map. Now, I am slowly I identify these ground control points. One thing which you will notice here is that these ground control points are spread all over the image, just 5 ground control points are demonstrated here. But what basically means here that if my image is this much, I should choose ground control points which are throughout my image area. It is not that all ground control points will be concentrated only in one corner of an image. Then it will give you a completely wrong georeferencing. Let me give you an analogy. Say basically you treat this satellite image or digital image as a rubber sheet. So if I have to fix this rubber sheet over a surface, then I will nail or put a tape on one corner, then another corner opposite direction, then another two more corners on opposite direction. Then in between might be that rubber sheet may not be fitting very well. So again I will use few more tapes or few more nails or few more GCPs, ground control point, so that it uniformly my GCPs are distributed and I get best fit. So that is why these ground control point should be spread all over the image rather than concentrating in just one area. So number of ground control points one should go multiplying by 2. So generally we go for third order or polynomial equations, minimum 10 points, choose 20. And the advantage nowadays, because of this technique is becoming very user friendly both in digital image processing in GIS softwares. So once you choose 2 or 3 initial ground control points, the system itself start predicting about as soon as you go for the fourth, the values, these means the coordinates it will predict, and it is sometimes quite good. So one more important thing, the initial ground control points which you choose, you should have a very high level of confidence in it. So whenever you are going for georeferencing, make sure that the first few initial points, they should be very far apart from each other, one, and they should be highly reliable ground control points. You are having full confidence that you are rightly identifying that ground control point on the image as well as on your master map. So once you are having confidence of that level, then these softwares which will predict for future ground control points and the geographic values are going to be very accurate, and then later on your whole process will become much easier. The maximum time the software will take, or in this technique, the maximum time should be spent to collect very nicely, very accurately the ground control points, because then next 2 steps are has to be done by the computer, and nowadays it's not very difficult. It's very quickly you can do it then. So you must spend a lot of time so that you very correctly, very accurately precisely you collect these ground control points. Once the transformation is found through these polynomial equations is applied for each pixel of the input image. So after the ground control points, then you choose the appropriate polynomial equation. Say I have chosen the third order, I have collected 20 points. Now I am having also at the same time I will have error table also. In these softwares you will get error table. So you would know exactly that which ground control point is giving better accuracy or having more error. So the point which is having maximum error, I may reconsider it, means I may remove it and collect it. In that way I can further improve my georeferencing. So these tables are used to assess my accuracy part of my registration through using these ground control points. Once I am okay with that, then I go for this transformation function. The other operation to perform when doing a transformation of this type is determining the pixel value. That is the resampling, the third step, last step in georeferencing. And this is accomplished by using these resampling techniques. There are 3 types: nearest neighbor, bilinear and cubic convolution. We will discuss all these 3 one by one. So the transformation can be represented by a polynomial order. This is a generalized polynomial equation. As per a given order, you can calculate or estimate the x and y for your the slave image for that corresponding ground control points. And then once this is available, then like for example, I am giving a example from ArcGIS software, that is the image to word transformation, which is a GIS software, is to 6 parameter affine transformation, that is the second order polynomial equation in the form of these equations, very simple one, and I will describe all these one by one, these equations that here is the image, and here is the master image, here is my slave image, and this in equation the x1 the calculated x coordinate of the pixel on the map, and this is y1 the calculated y coordinate on this one, and then x and y are the column row and row number of my input image, and these are of my target map. And then I am having a, because the second order polynomial also will allow me to transform, not only transform from geometric domain to geographic, but it will allow me to change scale. So in my equation I am also having a, that is scale dimension of a pixel in a map units in x direction. Then I need to have b and d, and that means the rotation terms, because it the second order polynomial also allowing you to rotate the image, not only allowing us to change the scale, not only transforming from geometric domain to geographic, but also rotation. And then C and F are the translation terms, that means x and y map coordinates of the center of upper left pixel. And then also one more thing is the negative of y scale, because remember I mentioned that in a slave map or image, scanned map or an image, the coordinates starts from top left, whereas in a georeference map the coordinates will start from bottom left, and therefore this negative of E is plays also very important role of y scale, that is dimension of a pixel in a map units in x direction. So that has to be also accommodated in my scale. This y scale negative, as I have just explained to you, is because of the origin of an image and a geographic coordinate system are different, and the origin of an image is located in the upper left corner, whereas the origin of a map coordinate system is located in the lower left corner. Now about interpreting these errors, which once we choose the appropriate polynomial equation, we get the error estimate. So how you choose these errors is that when the general formula is derived, they applied to the control points, a measure of error, that is residual error, is returned, and this error is nothing but the difference between where the point from ended up as opposed to the actual location that was specified to the point position. And the total error is computed for each GCP's error is calculated, for total it is also. Total is also useful because we would like to see whether I am within a 1 pixel depending on the spatial resolution. So if I am having a 50 meter resolution data, then I need that my error in mapping scale should be less than that, this total RMS, root mean square error. And if I am getting that error which is less than say 50 meter, then I am sure that I am having within a pixel, and that is the best, because pixel is nothing but a unit, and a unit means indivisible, and I cannot go beyond that. So if I am achieving georeferencing or this error within 1 pixel, I am achieving quite good georeferencing. So this error value describes how consistent the transformation is between different control points. Also in some softwares like in ArcGIS, this difference is also called links, and when you will do in such softwares, these links are shown with the color. So if it is coming green, that means your link is good. If it is coming in red, that means that particular GCP you have wrongly collected, and therefore it is showing more errors. And when the error is particularly large, you can remove, add a control points to adjust the error. So it is a continuous process. Once you have collected say 10 points, now you look for individual points and corresponding errors. The point which is giving maximum errors, you may remove it, again recollect it, and if it has improved, then look that which point is giving the maximum error, and likewise you can keep improving till you reach within pixel. And although RMS is a good assessment of the transformation accuracy, don't confuse as a low RMS error with an accurate registration, because when for example the transformation may still contain significant errors due to a poorly entered control points. So remember this thing, if you have collected control points only in a corner of an image, then you will get a small RMS errors, and you would think that I have achieved a very good registration using control point, but in fact not. So that is why I have mentioned that your ground control point should be spread all over your input image. More ground control point, that is why I mentioned that multiply by at least factor of 2. So more ground control points of equal quality means highly accurately collected with a high level of confidence that yes, these two road crossings is the same as I am seeing in satellite image as in my map, master map, and used for accurately, the polynomial can convert the input data into output coordinates. In the previous lecture I have mentioned that nowadays the Google Earth has become more or less a standard product, and for high resolution satellite images the ground control points we can also collect from Google Earth by zooming it, and once I am sure that that is the corresponding point which I am seeing in my raw image yet to be georeferenced, I will collect those coordinates x and y and put against my image. So in that way I may achieve a much better georeferencing. There are other ways also. I can go in the field. I have identified these ground control points initially on my satellite image. I will go in the field, collect my ground control points coordinates very accurately, maybe using even differential GPS. So once I have collected ground control points really on the ground, their coordinates, then my level of confidence in my georeferencing is going to be very high. These are required once we go for very high resolution spatial data or very high resolution satellite images. But if you are using relatively coarser resolution satellite data, probably going in the field and collecting ground control points or the coordinates of ground control points may not be required. So whatever available resources you can use, especially the Google Earth and some master maps, already georeferenced satellite images, and then can collect the GCPs, corresponding GCPs, and can get the georeferencing done. So this will convert into output coordinates. Now the last step in georeferencing, that is resampling. As I have said that there are three techniques in resampling, but in simple one view graph I can explain to you all three, and think that this is going to be the one which is mentioned here is geometrically corrected matrix. This is yet empty matrix, means after knowing the transformation function, now I know that this a particular pixel has to move. Say for example pixel 1 which is marked on uncorrected matrix has to be moved in the shaded area of a corrected matrix. Then what should be the value of pixel? One is the location of pixel where it has to move, and what is going to be the value, whether original value I am going to keep or I am going to change the value. Why the change is required we will see once we go in the second and third resampling technique. In the first resampling technique, that is the nearest neighbor, in which what we do that whatever the value pixel 1 is having, suppose it is having a value in a 8-bit image, it is having value of say 150. Now I will have the system will have a look that which out of these 4 which are overlapping the shaded pixel, which one is having the maximum overlap. What I will find that the pixel 3 on this uncorrected image or matrix is having maximum overlap on my target pixel, and therefore it will have the whole weightage. That means the pixel value, say 3, whatever a 3 is carrying, maybe 200, will be directly transformed to the shaded pixel of my corrected matrix. So the pixel which is having the maximum overlap will have the full influence, and this way we achieve the resampling, which we term as nearest neighbor. We will see little more details about this. Let us go for the second one, that is bilinear, in which what is done, that as you have seen that this shaded pixel is having overlap by uncorrected image marked 1, pixel 2, 3 and 4, having overlap of different size of areas, like 2 is having minimum, 3 is having maximum, and 1 and 4 probably of having same. So now I can use the weighted average concept and say that the pixel whichever is having the maximum overlap will have the maximum weightage while calculating the pixel value of my target cell or target pixel, and the pixel which is having less overlap or minimum overlap will have the minimum weight, and therefore it will have less influence on the target pixel. So in this particular example, the pixel 3 of uncorrect matrix will have maximum influence over this shaded pixel than pixel 2 which is having minimum. So all 4 pixels as per their overlap will have their weight while calculating the pixel value of the target pixel, and this technique is called bilinear. Now remember, when we started with nearest neighbor, only the pixel which had the maximum influence carried the whole value, but here now 4 pixels are involved, and therefore you have to think the same time what is going to happen to the image quality. On that I will come little later, but let us discuss the third resampling technique, and that is your cubic convolution. So in which instead of involving 4 pixels, now 4 by 4 matrix, all surrounding pixels, even the far distance pixels of will be used on distance weighted average. So the pixel which are having maximum overlap and their minimum distance will have the maximum say while deciding the pixel value of the target pixel, and the pixel which is very far having large distance, no overlap, will have a minimum say while or minimum influence while deciding the pixel value, and this kind of resampling technique is called cubic convolution. So if you compare with nearest neighbor with cubic convolution, you would realize that too much averaging of pixel is done for target pixel. Using 4 by 4, that means 16 pixels are involved to determine a pixel value for a target pixel. But as per requirements, these 3 techniques may be chosen. But if you are only looking for highest quality of image, do not want to compromise on the quality of image, then the nearest neighbor you would find the best combination. So in nearest neighbor resampling, which determines, as I have mentioned, the pixel value from the closest pixel to the input coordinate specified and assign that value to the output coordinate and or output pixel. So the pixel which is having maximum overlap will have the entire say, entire influence. This method is considered the most efficient procedure because it does not have to look the other 4 pixels, then weighted average calculation or other thing, or like in cubic convolution 16 pixels are involved, the distance is measured, weighted average is calculated, then a new pixel value is found. So that much of calculation is not required. That is why it is very efficient, nearest neighbor, in terms of computation time. Nearest neighbor does not alter the pixel value, especially when you are going to use these georeferences images for image classification. Then nearest neighbor is going to give you the best output while you go for classification, because if you go for cubic convolution and then classification, you may introduce some errors during classification. So in that way this technique is also good, looking for the future use of that particular image which you have just georeference. So nearest neighbor will not alter your pixel value. If desirable, if it is subtle changes in the pixel values need to be retained, then you go for nearest neighbor, and this method however induces a small error into the corrected image, especially it is might be offset especially by half pixel, because there might be some stair steps kind of or staggered appearance in the image, because you are just lifting a pixel value and assigning to another pixel without considering the neighborhood. And the corrected image may be jagged or blocky in appearance if there is much rotation or scale changes there. So if it is a simple transformation from geometric to geographic, that means first polynomial order, then there may not be any complication. Now bilinear, the second one as mentioned, that determines a weighted average of 4 nearest pixels in the corrected image, and these 4 pixels are in bold. And the closer the center points of pixel, the greater contribution or weight it will have for the final digital number or pixel value to be assigned to the corrected pixel. And this way the bilinear sampling resampling generates a smoother appearance resampled image compared to a nearest neighbor. The pixel value is altered in the process because now 4 surrounding pixels or overlapping pixels have put their influence while determining the pixel value for the target pixel, resulting in a blurring or loss of image resolution. So as I mentioned, if you are going for very accurate, looking for very accurate image classification, then perhaps nearest neighbor might be good. Even bilinear can work, but cubic convolution may not give that kind of good results, but will have a very smooth appearance. And this method requires 3 to 4 times the computation time as compared to nearest, because in nearest method once the maximum overlap pixel is found, that value is assigned, no calculation. But here weighted average has to be calculated using 4 pixels, and therefore computation time is going to be 4 times. Highly accurate registration will achieve more faithful pixel values. So if your first step is very accurate, then you will achieve better results in the last step. And last one in this resampling technique is cubic convolution, and this more sophisticated method, because it involves the 16 surrounding pixels of uncorrected image to estimate the pixel value for the target pixel. And therefore of course it is going to be much more computer intensive, that it is closer to the perfect sin x over x resampling than the nearest neighbor or bilinear, and avoids disjointed appearance, very smooth appearance as compared to nearest neighbor, which will have a jagged or stair steps kinds of might have. Whereas this will provide the cubic convolution, provide the more smoother results, but may not be appropriate, very appropriate for images for which are going to be for classification. And it provides a slightly sharper image than bilinear, but it also corrupts the original pixel value. Altered original pixel value is completely altered, having influence of now 16 neighboring pixels. And this method is not recommended, as I am mentioning. The classification is to follow, as the new pixel value may be slightly different than the actual radiance values detected by the satellite sensor, and the computation time is going to be more than 10 times than compared to nearest neighbor method. So this brings to the end of this georeferencing technique, which is very important and common technique between remote sensing and GIS. If all 3 steps are followed very carefully, then one can achieve a very good georeferencing, and anytime you can check your results of georeferencing by putting your images or maps which you have georeferenced on Google Earth. So that if it fits with the surroundings, you are sure that you have done a good georeferencing. So good luck, thank you very much.